You know that invisible force that powers literally everything in our world, from the lights above your head to the phone in your hand? We call it electricity. But what is it, really? How does it actually work? Well, we're going to pull back the curtain and take a look at the hidden flow that runs our lives.
Okay, this might sound like a weird riddle, but I promise it's not. The secret to getting your head around electricity is realizing that it acts a whole lot like water. Stick with me, and you'll see how the exact same ideas that make a waterfall work can explain the power flowing into your home right now.
So, first things first, if we're going to say electricity is like a river, then we have to ask, what's the water? What's the actual stuff that's moving through all those wires? Let's break it down. That stuff is called charge. Just think of it as the individual molecules of water in our river. It's a basic property of all the tiny particles that make up, well, everything. We measure it in something called coulombs, but honestly, don't get hung up on the word. Just picture these teeny tiny packets of electrical energy. All right, so if charge is the water, then current is all about how fast that water is flowing. It's not the substance itself, but its movement, that continuous stream of charged particles zipping through a wire. And we measure this flow in amps, or what you've probably heard called amps. It's just like thinking about gallons per minute. A fire hose has a way higher flow rate than your garden hose, right? Same deal here. A high amp circuit just means more charge is flowing past a point every second. In fact, 1 amp is officially 1 coulomb of charge passing by in 1 second. It's as simple as that. Okay, so we've got our water, which is charge, and the speed of its flow, which is current. But what makes it flow to begin with? And what's trying to stop it? Well, this is basically a story of two forces working against each other, a push and an opposition. So the push is called voltage. The textbook definition is that it's the energy needed to get each little packet of charge moving. But that sounds a little academic, doesn't it? So let's make it super clear with our water analogy. Imagine you have a closed loop of pipe, totally filled with water. The water's just going to sit there, right? But if you add a pump, it creates pressure and forces that water to start flowing. In a circuit, a battery is that pump. Voltage is the pressure it creates. It's the force that gets the current moving. But that flow isn't always on a smooth, easy ride. In every single circuit, there's a force fighting back, trying to slow the current down. We call this opposition resistance, and we measure it in ohms. Imagine your big, wide pipe suddenly gets squeezed down into a narrow little section. The pump, or voltage, has to work way harder to push the same amount of water through. That's exactly what resistance does. Some materials, like copper wire, are like wide open pipes with super low resistance. Others, like the tiny wire inside a light bulb, are like a very narrow pipe with high resistance. And this whole idea gives us a really simple way to sort circuit parts. You have active components, like batteries. They're the pumps. They add energy to the system. Then you have passive components, like resistors. They're like the narrow pipes or the water wheels. They only use up or get rid of that energy, usually as heat or light. So we have pressure, which is voltage. We have flow rate, which is current. And we have the narrowness of the pipe, which is resistance. How do these three things all relate to each other? Well, lucky for us, there's one simple, elegant rule that connects them all. It's called Ohm's law. This guy, George Simon Ohm, figured this all out ages ago. And what he discovered is actually really intuitive. He basically said that if you increase the push, the voltage, then the flow, or current, also increases. And if you increase the opposition, the resistance, then the flow decreases. Makes perfect sense, right? And it all boils down to this fantastic little formula. Voltage equals current times resistance. V equals I times R. This is the secret recipe for basic electronics. If you know any two of these, you can always figure out the third. It's the key to understanding pretty much any simple circuit out there. Okay, let's see this in action. Your toaster works by pushing current through a resistor, which gets super hot. So we know the resistance of that heating part is 15 ohms, and we know the voltage from a typical wall outlet is about 110 volts. So how much current does it need to make your toast? Well, we just rearranged Ohm's law a little bit. Current equals voltage divided by resistance. We plug in the numbers we know, 110 volts divided by 15 ohms, and we get our answer, 7.33 amps. It's that easy. You just analyzed a real-world appliance. Now, Ohm's law is perfect for a simple, single loop. But what about more complicated stuff, where wires are branching off all over the place? Kind of like the wiring in your house. For that, we just need a couple of rules of the road, called Kirchhoff's laws. The first law is all about junctions, or intersections. So picture a spot where a few pipes meet. KCL just says that the total amount of water flowing into that junction has to equal the total amount of water flowing out. Current can't just appear out of nowhere or disappear into thin air. It has to go somewhere. The second law is all about loops. It says that if you trace any closed path in a circuit, all the voltage boosts you get from things like batteries have to be perfectly balanced out by all the voltage drops you get across things like resistors. So by the time you get back to where you started, the pressure level is right back to zero. Now, it's good to know these laws have a little fine print. They work perfectly for most circuits we deal with every day, but they do assume a few things, like that there isn't a crazy magnetic field nearby. But honestly, for 99% of everyday electronics, these are the essential rules of the road. So we've gone through the basic rules that control the flow of electricity. But why does any of this actually matter outside of a classroom? What's the real-world payoff for knowing this stuff? Well, it all comes down to one huge word: efficiency. Take a look at this. An old-fashioned 100-watt incandescent bulb, the kind that gets really hot, draws about 0.45 amps of current. Now, a modern 15-watt LED lamp, which gives off the same amount of light, draws just 0.068 amps. The difference is just staggering. Let me put that another way. That old bulb needs 6.6 times more electrical flow, more current, to do the exact same job as the LED. That's all just wasted energy, wasted money. This is why it matters. Understanding and controlling this flow is the absolute key to designing the efficient technology that's going to power our future. So we started with a simple question about a waterfall. And now you have the fundamental rules that govern everything from your toaster to a tiny LED. That hidden flow isn't so hidden anymore. So the real question is, now that you know the rules, what